Welcome back, everyone. And as promised, we're moving into a slightly different topic area now, a non-intrusive solution for monitoring ship cavitation phenomenon. And I'm really delighted to have with me from TSI, Aquilino Alvarez Castro and Luis Piqueras Gonzalez Tejero. Gentlemen, looking forward to your presentation. Over to you.
Thank you. Okay, thank you. So, hello everyone, and thanks you for attending this presentation. I'm Luis Piqueras, Naval Engineer in the RDI department of TSI, and with me is Aquilino Alvarez, Director of the department. And we are going to present the NI-CDS system, which aims to bring the interested parties an easy-to-use and install system cavitation control, developed by TSI. So, first of all, here you can see the index that we are going to follow, starting with a description and basic aspects to take into account with the cavitation phenomena, passing then to a presentation of the system itself. So without further dilations, let's start. As I said, first of all, we need to understand what is the cavitation and why it occurs. Normally, thruster and propellers in the naval ships, in order to move the ship, create pressure gradients around them that translate into forward or backwards force used by the ship to move it itself. These pressure gradients are a fundamental part of the operation of the propeller, but they have a secondary effect. In areas where the pressure gradient is excessive, either by operating conditions, improper designs, or because any other reason that can appear, the water begins to boil at normal sea temperature, producing water vapor bubbles. These bubbles, when moving away from the propeller and entering normal pressure zones, implode, producing largest amounts of noise and vibrations. This is what we call cavitation. Here in the superior imaging, we can see the mechanism that the cavitation follow to erosion the surface of the blades in a propeller. And in the lower, we can see a pressure temperature diagram corresponding to the water. The yellow triangle shows the normal sea condition, more or less 1 atmosphere and 20 degrees Celsius. When the thruster is in operation, the pressure drops, following the blue line, entering the vapor zone and causing the vapor bubbles to appear. Okay, as we have said, the vapor bubbles, when imploding, produce large amounts of noise and vibrations. We have a series of effects that on the ship itself and its elements, on the environment also. Among these effects, we can highlight 4 of them. The first of all is the noise and vibration going through the hull, decreasing the comfort inside the ship. The second is the extensive damage to various elements, such as the propeller blades, or even the rudder, caused by the erosion produced by the imploding vapor bubbles, as we said before. Here in the first imaging, we can see a fully developed cavitation situations with bubbles coming out the propeller, and in the next imaging, we can see the damage produced by the phenomena. The first effect that we can highlight is a decrease in the propulsive performance of the ship, since the propeller is not designed to operate in a steam mixture that absorbs part of the transmitted energy by the engines. Last but not least, cavitation noise can be very disruptive to some marine species, such as cetaceans, causing reductions in their population. Now, related to the types, there is no a single type of cavitation. And in fact, its effects and severity vary according to the type of phenomenon that is occurring. There are 7 main types of cavitation. The first of all, and more typical, is the bubble cavitation. It's produced by propellers with high curved blades. It's distinguished by big bubbles produced by the high pressure drops that produce great amount of noise and vibrations. The second one is laminar cavitation, normally presented in propellers with high angle of attack, making difficult to the flow follow the surface of the blade. Typically, it produces very low noise and vibration levels, being a vapor vein that follows the blade of the propeller, also cause little damages. The third one is the root vortex cavitation, that depends on the geometry of the blade roots. is less common than the other types and normally is unnotized. The fourth one is the cloud-type cavitation, produced by the detachment of a laminar cavitations. Consists in little bubbles coming out of the propeller with great amounts of noise and can affect also the rudder. The fifth one is the propulsor hull cavitation, caused mainly due to the interaction of the hull flow and the blade between the blades and the hull itself. The sixth one is the tip vortex cavitation, that is similar to the root vortex cavitation, but produced at the tip of the blades. And last, the core cavitation, that is very similar to the previous one, but with low effects, and it appears in the center of the core of the propeller. Now, related to the monitor of the phenomena, due to the nature of the cavitation phenomena, and when it occurs, it is usually difficult to observe the phenomena without the use of auxiliary means. Normally, we use two principal methods to study this phenomena. The first of all, we can see in the left image, is consisting windows installed in areas of the hull near to the propellers, making it possible to observe it from the inside during the operation. The second one consists in cameras placed in the outer face of the hull, oriented adequately to be able to record the phenomena. Both of them require the vessel to enter dry dock for installation, with the consequent cost derived from immobilizing the vessel and the modification itself. Also, it's necessary to make physical modification of relative importance to the hull itself, as well as in some cases to the structure of the ship, with the consequent impact on the classification of the ship and also the safety of it. Both methods rely on physical and imprecise observation and assessment of the cavitation, which requires the ship to go through as many sailing situations as possible, not only the typical ones. Any case of situation that is not observed will be an unknown point of operation. Now, with all the bases explained, I give the word to my colleague Aquilino, who will present the system with its main characteristics, operation, and advantages. So, Aquilino.
Thanks, Luis. As Luis said, my name is Aquilino Alvarez. I'm Director of Research and Development at TSI. Just go to the next slide, please. Yes, indeed, looking at all this, let's say, interesting understanding cavitation, TSI started to work on this idea of the non-intrusive cavitation detection system, which actually what we looked at is not to avoid cavitation, but better is to understand its occurrence and intensity. Okay, so this system actually aims at providing essential information to crew members on how to deal with the phenomena when they're sailing on different environments. So next, please. So just to go through how the system is structured, we place several sensors across the hull, different areas previously identified. And then all that data go through, let's say, an algorithm that we have developed. And then all the results are shown in an ad hoc developed user interface, which actually is what helps the crew members or even the engine staff to see in real time what is happening in respect to the propeller performance, and indeed to see when cavitation starts to occur. Next, please. So it's worth mentioning that before starting this development, we had to identify which were the requirements for the system to be, let's say, successful in technical terms. So there were two key aspects we identified in terms of requirements. As Luis mentioned before, the current systems requires that some, let's say, not requires, but forces to implement modifications in the hull. So, and this a part of being expensive, it also requires that the ship has to be stopped and put in dry docks to make those modifications, and then of course to ask the different classification societies to certify that the ship still has complies with the requirements for being the sea again. So of course is a mandate, let's say a key requirement for this development was that the whole system needs to be non-intrusive, so no hull penetrations or holes. And of course, the less, let's say, intrusive activities like putting the ship on dry docks and so on. And then, of course, the last one is as many, let's say, hardware, software components that the ships uses for assessing the sailing operations. The system need to have some self-calibrating requirements. So using, let's say, commercial available sensors, but at the same time, the algorithm we developed need to provide a sort of self-assessment that adapts the data processing to the specific vessel and sailing requirements. Next, please. Similarly, there were other types of requirements that we took into consideration, like the system need to offer the possibility to be a standalone system or an integrated system with other subsystems already existing in the vessel. Of course, a sort of like plug and play system, which not too much configuration requirements, or let's say software adaptation to other operating systems already existing in the vessel. Then, of course, friendly user interface. All the data must be recorded on a continuous monitoring process. All this data need to be available for statistical purposes, but because, of course, each vessel has its own characteristics, and of course for future let's say designing or operation strategies, all these data need to be recorded somehow for future statistical analysis. And as I said before, the calibration process need to be flexible and self-adapting. And of course, like any other system, the reports and the data can be easily exported. And of course, like any other system, has to be flexible and customizable according to each customer's need. Next, please. Then I make a hard turn because I think to explain some of the data that the system records, I want to go through directly the user interface, especially on two specific areas of the system, which that shows the performance of the propeller, and then some advanced settings. Next, please. The system reflects the results through this dashboard. We are showing here as an example of a trim propeller vessel. All this information is from a real vessel we already monitored. So you can see that from the one hand, from one side, we are recording data from the shaft and the propeller pitch, and then this data is compared to what we have called the cavitation index, which is shown in the red line of the graphs on the right side. Go to next, please. So in these graphs, you see the historical evolution of the propeller performance and where cavitation start appearing. Okay, so as I said before, it's not the system doesn't allow to impede the appearance of cavitation. the system only helps the crew to understand in which situation this phenomenon starts occurring. So this is very important. For instance, in situations like this is very important, for instance, for military vessels. Okay, when the still sailing modes are required, so they can modify the sailing patterns and reduce the acoustic signature. Next, please. Similarly, we have here the time domain data from the accelerometers, and the data processed to show the spectrum of the propeller. Okay, so in the lower line, down below, there's the blue graph. When you see the time domain evolution of the frequency intensities, okay, and when the cavitation starts appearing, different harmonics also start appearing in the graph. So this is a complementary information that helps also the crew to see in more detail, or let's say with more accuracy, when the different types of cavitation starts appearing. Next, please. In a similar way, we can also show the different performance of the accelerometers. In this case, we place 6 different accelerometers. This is not mandatory. The number of accelerometers, it will depend on the type of vessel. But what we consider is important is that each accelerometer shows the sensitivity they have on indicating when the cavitation phenomena starts appearing. Then also it's also important for that's what we think, for the crew members to have a record, like you see in the bottom left side of the dashboard, the self-calibrating process depending on the current sailing conditions. Okay, next, please. So probably you may wonder if we actually have proved this system in different situations. So the first, let's say, experimental validation we performed with our system was in the CEIPAR, which actually is a research institution mostly dedicated to marine studies. So they have this cavitation tunnel in which we actually made the first experimental validation of our system. So next, please. So we place the different accelerometers on different parts of the let's say the external part of the tunnel, and we compare the results that we got with the different systems the CEIPAR has for controlling, let's say, the propeller performance. And what we, let's say, managed to get is very similar patterns with our system, with the system they have already installed. So that gave us a lot of confidence of the data processing inside inside our system. Next, please. We actually did another test campaign with a slightly differences, okay? Because of course, as I said before, there's an ad hoc processes before installing the system to understand the asset in which we're placing the sensors. But with a slightly difference, our system proved to offer similar values. Okay. So next, please. So we actually went to 3 different in situ pilot testings. Okay, none of the graphs corresponds to the vessels because of confidentiality, let's say, issues we have to comply with. But still, the results we obtained prove the system actually shows indications on where the cavitation for each vessel starts to occur. It is also worth mentioning that we did this pilot testing within the Aqua project, which was a European research project funded by the European Commission under the 7th Framework Program. And even though this project finished on 2009, we continue doing some pilot testing, and actually we're doing a pilot for the Spanish operator Balearia. So we are confident in the results we will get from this pilot testing. Next, please. So just to mention the key benefits of this system is, of course, understanding cavitation increases the lifetime of the vessels because it reduces those harmful effects of the cavitation on the propeller and the hull. It provides accurate control of this phenomena, and actually in terms of the environmental impact of cavitation, it also allows operators to reduce or to manage let's say the speed of the vessel in some noise restricted areas. Okay, of course, it allows, or let's say it contributes to manage the onboard vibration level, and in general terms, it improve performance and, let's say, optimize the fuel consumption of the vessel. As I said at the very beginning, it's a non-intrusive installation, which I think is key for our industry to, let's say, foster these kind of systems. For the military, of course, for the navies, it allows to properly manage the silent modes, and definitely we think it's a very cost-effective system. And next, thank you. I think that's all, and I hope you find it interesting.
Thank you so much. Excellent presentation. Really enjoyed it. We have one question in the chat from Ronald Welsh from the TS Queen Mary. He asks, how do you determine where the sensors are located?
Okay, I will answer that question. Normally, the system is very flexible in terms of the location of the sensors. But the first thing that we do when a customer asks for this service is to study all the structure of the ship to determine which place is a better option to place that sensors.
Okay, thank you. And is this, do you envisage this being installed permanently as a system, or is this a sort of diagnostic tool that you'd employ sort of as and when?
Well, it can be. I mean, you can use it in both ways. It depends of the, let's say, in which stage of the life cycle the vessel is. If it is a new vessel, it can be installed permanently. But as you say, it can be also used for as a diagnostic tool. Mm-hmm. So you can leave it a certain period of time, you understand what is happening, and then you can make a sort of assessment on the vessel performance in terms of the cavitation.
Thank you. And in terms of giving owners and operators access to data they can make a decision on, and I'm talking now about, you know, do they need to change materials, components, parts of the system out? How easy do you think this would be for people who are non-engineers ultimately to be able to make a decision?
Well, actually, I think I mentioned something about it during my part of the presentation. Of course, it is important to have some engineering at the background for understanding what is happening. Okay, but at the same time, we have developed the system for people not familiar with the matter. Okay, just to provide insightful information to crew members in order to manage the situation, just to provide them with insightful information. Okay, so and then of course all that data can be used later for more specific engineering purposes. Okay, yeah. But you don't have necessarily to be an expert on the matter, neither to manage the information, and of course neither for future calibration and so on.
Yeah, Thank you. It's good to know, because that's obviously the application end of it and how people can make a difference, because it's looks like a fantastic presentation. Really can see the application of it. So thank you so much. We are out of time and we have no more questions, but it's been a great presentation. Thank you so much, both of you, for coming along and giving your time today. Really enjoyed hearing you both speak. I hope you enjoy what's left of today's conference event, and you're able to sneak off and go and have a rest now, having presented.
Yeah, hopefully. Thank you very much, Sarah.
Brilliant.
Thank you very much.
Nice.
So, ladies and gents, we are very nearly at the end. We have one more presentation to go, and we're into advanced additive manufacturing in shipbuilding. So we will close this session here and reopen on another channel. So I will see you there shortly. Brilliant. Thank you.